Hi, let's do this problem. Welcome back. Great job. As we discussed yesterday, if an object has momentum m times v, that'll change when there's force. Like, look at this baby right here. How do I give the baby momentum? By applying a force. The force I apply times the time the force is applied is equal to the change in momentum. Impulse is change in momentum. Lots of fancy words, but pretty straightforward equations. Okay, time for a big brain moment. If I have a baby and I apply no force, what will happen to the baby's momentum? If I have an object and I apply no force, what will the change of momentum be? 0. Yes, very good. F is 0, delta P is 0. That's true for a stationary baby. It's also true for an asteroid. That's like, that's actually where the moon goes. It's true for a baseball being thrown through the air, not through space. If I find its mass and its velocity, and I apply no force on it, the mass will be constant and the velocity will be constant, so the momentum m times v will also be constant. What's the point of that whole lesson? I'll tell you. How would we find the velocity of this? I have a $4-kilogram blob of clay moving at velocity 3 meters per second, and it hits a $2-kilogram block of ice on a frictionless surface. They stick together. So now I got the blob stuck to the ice, clay, ice. How fast will it slide away? That's the problem. Clay hits ice, stick together. How fast will it slide away? Alright, well, if you had to do kinematics, this would be impossible. You have to find the force from the clay on the block, and then the time that force was applied, and then you have to find the acceleration, and then find from the initial velocity, find the final velocity. But then you have to do the same thing for the clay too, because the clay has some initial velocity and experiences a force, and it also accelerates. You do know at least that the velocities afterwards are the same because they stuck together. So that's a nice little clue, but you'd have to find the force, the time, the acceleration, and the initial velocity to find the final velocity, which is just, that's too much work. We're not doing that. You need to have a large brain realization. Does the mass of the clay? No. Does the momentum of the clay change? And also, new question, does the momentum of the ice change? Yeah. The clay hits the ice, it's going to slow down. But the ice, if it starts at rest and it starts moving, it's going to speed up. So both things change. P clay will decrease, and P ice will increase. The clay hits the ice, it will slow down. the ice gets hit by the clay, it'll speed up. So P clay drops, but ice rises. Cool. Not good. It's a complicated problem. What are we going to do? Look at these. Think of what can we realize about P clay and P ice. Here's a hint. What can we realize about delta P clay and delta P ice? We know the clay will slow down and the ice will speed up. But do you see any relationship between these variables? Tell me right now. Some people will say they're the same. Not quite. They're vectors. The momentum of the clay to the right will be less. The momentum of the ice to the right will be more. So they're the same magnitude, opposite direction. That works. Another way, you can say the total is 0. The sum of these two changing momentums are 0. They both change. But if you add the changes, one to the left and one to the right, or one positive, one negative, they will cancel out. So that's fine. Another way to think of this, these values both change, but P clay plus P ice is, well, we don't know what it is, but we know it's constant. This changes and this changes. This decreases, this increases. But since the change sum is 0, the total is constant. This is known as conservation of momentum. Not to be confused with conservation of energy, but it's basically the same idea. If there's no work done on a system, then the amount of energy in the system doesn't change. If there's no impulse on a system, then the momentum of the system doesn't change. Oh my god, wait, what? Hang on. Did I just contradict myself? I said there's no impulse. But isn't there impulse? The clay pushes the ice, and the ice pushes the clay. So there is force, and I'm sure those forces are applied for some time. Collisions take time. So how can this be true? This be true. How can the change of momentum of the clay and ice be 0 if the clay and ice do exert forces on each other for some time? So the question is, if there is force and there is time, how can delta P still be 0? Ooh, I know, Mr. Lyon. Yes? What is it? Newton's third law. Oh my gosh, so smart. Yes. There is a force from the clay on the ice. There's a force from the clay on the ice. And there's also a force from the ice on the clay. But due to the third law, they are opposite. I didn't say they cancel. They are opposite. If you look at just the clay, they don't cancel, because this is the only force you care about. If you look at just the ice, they don't cancel, because this is the only force on the ice. But here's the big idea. Treat the whole thing as one system. We don't care about P clay or P ice. We care about P clay plus P ice. I should pick something that would stick. Ice and clay might have to stick together, but not important. The two forces are equal, and the time. Any ideas? The times are also equal. Yeah, that's right. The time that the clay exerts force on the ice is also the same as the time the ice exerts force on the clay, because that's when they're touching. So there is delta P, 2 delta P's, but they will add up to 0 because the force between the clay and the ice is what's called an internal force. It's from one object on the other object. If we care about both objects together, the force from one on the other doesn't affect the momentum of the system. Hopefully that makes sense. If we look at just one object, that force matters. But if we're analyzing momentum of P clay plus P ice, then the force between the clay and the ice doesn't affect the total because it'll cancel out on the equation. Wow, amazing. Let's solve this problem. We don't need to find this because we only care about the total. The total in the beginning is 4 times 12 kilogram meters per second to the right. Remember, it's a vector, so we need to include direction. So the momentum of the clay is this. The ice starts at rest. I probably should have said that earlier. The ice starts at rest. So this is not the momentum of the clay. This is the momentum of the system before the collision. Let's call it, P. No, let's call it P. P naught. That means it's also the momentum of the system afterwards. So after the collision, the clay and ice move together, and we know their momentum is still 12 kilogram meters per second. How do you find the velocity if you know the momentum? Oh yeah, I heard you say it. Great job. The momentum is m times v, so it's the total mass, 6 kilograms, times v. V is 2 meters per second. It's 12 over 6, and the direction is maintained. So this is a conservation of momentum problem. There's lots of examples of conservation momentum problems. Usually they involve two things hitting each other, a collision, or two things separating from each other, where it's called an explosion. It usually doesn't involve like a big fiery ball of death. It's usually like a sailor jumps off a boat, or like a cat jumps off a skateboard, or even like a girl on a frictionless pond will throw a rock. That's an explosion, because if someone's throwing a rock, they're applying a force on the rock's applying the same force, remember, same force, back on them. So if you're on like a frictionless ice skating rink and you throw a ball, in theory you will go backwards. And the momentum of you plus the ball will be constant. So I did a practice problem. There's lots of examples. I did a great job in this lesson, pretty much. Yeah. Main idea is if there's no external impulse, internal forces, internal impulse is okay. If there's no external forces, like my hand doesn't come over from outside the system and push the clay, then the change of momentum of the system will be 0. And you can use that in a variety of ways that you'll see in some practice problems. One type of practice problem you might see, we actually saw when we used energy, a perfectly elastic collision. So let me write this out. Okay. Two objects hit each other, and then they bounce apart. Object A starts velocity VA naught. Object B starts with velocity VB naught. After they collide, then their velocities are VA and VB, not VA naught and VB naught. If you knew VA naught, VB naught, MA, and MB, but you didn't know these two, VA or VB, you couldn't solve it with just momentum, because there'd be two unknowns, VA and VB, and you only have one equation. But this problem is solvable if you had two equations, and you might. Some problems are called perfectly elastic collisions. Perfectly elastic means energy is conserved. Collisions means momentum is conserved. So you could see problems like this. I'm going to do a derivation. It's also in the book. If you are not interested, you can stop watching. That's okay. But if you were not here to hear me say stop watching, then I guess you got to watch because you weren't paying attention. Let's go. So delta K equals 0, delta P equals 0. It's very tedious. This is the conservation of momentum equation. See the momentum initially equals the momentum in the final state. NA, ND, the sum of ND, this is the sum of ND. Okay, so super crazy equation for conservation of energy, but same idea. The initial K equals the final K. We assume there's no springs or gravitational effects. And I'm going to erase all the 1/2 to make it slightly easier. Basically, I multiply both sides of the equation by 2. Okay. Move this over here, move this over here. You won't be asked about this on the test. But you might use this shortcut. In fact, it's probably pretty useful. I know what I'm doing. Okay, I separated these. That's the difference of squares. You guys know, like, a squared minus b squared is a plus b times a minus b. I did all that. And take this and rearrange it. And it's okay. So it's pretty messy, but we did it for the best. MA times the quantity VA naught plus VA times the quantity VA naught minus VA equals MB times the quantity M times the quantity VB plus VB naught times the quantity VB minus V naught. This is true because we got it from this equation. This is also true. This is a rearrangement of this equation. I subtracted this term and this term from both sides. Well, this term, this, is this. And this is this and this. So we can do some easy canceling. Sorry for the mess. That's the short. Alright, if you watched, hope you enjoyed or learned or followed. If not, well, then you're not here hearing me say this, so cool. See you in class.